So, good morning, and last time we started with a bit of sorting and in the process also verified the running time complexity of insertion sort, but there was a bit of, it was a bit unclear when I set up the function that told us how long the insertion runs, exactly how to set up that function. And so today I'll give a general recipe on how to do that. So let's focus. What's going on here? Right. So the principle will be to count function calls. And there's a precise method of how to do that. So for every function of a certain type, we define a timing function called t underscore f that takes the same argument types, but doesn't produce something of type nat, but produces something of type tau, but produces something of type nat, namely the number of function calls that were made when evaluating the function tf on those arguments. And the translation from f to tf is purely mechanical. There's no intuition involved at all. And how does it work? Well, we introduce a translation relation. This is squiggly arrow. And the first rule tells us how to translate defining equations. So if you have a defining equation for f of this form, you have almost the same defining equation for tf, but on the right-hand side, you have not e, but e prime plus 1. And what is e prime? E prime is the result of translating the expression e that was on the right-hand side of f into an expression e prime for the right-hand side of tf, for the timing function. So the squiggly arrow is overloaded. Down here it's used for translating defining equations. Up here it's used for translating individual expressions. And where does the plus 1 come from? That is simply, we also have to count the call of the function f. So the e prime counts how many function calls are made in the expression e, and then we add 1 for the function call of f that this equation represents. Make sense? Appears so. Then, how do we translate the individual expressions? Well, that's a syntax translation as well. So if you have a function call of some function g with arguments s1 to sk, so then you translate that into the time it takes to evaluate that function call. So first you translate all the arguments of the g, and you get t1 to tk, which are the times it takes to evaluate the arguments s1 to sk. Then you add all of them together, and you add the time it takes to evaluate the call of function g on those arguments. So it's just a bottom-up translation of the expression g of s1 to sk to a corresponding time expression that adds together the time required to evaluate that expression, consisting of the time for the sub-expressions plus the function call itself. That's almost all. So that questions on the general principle here. Then there are some special cases, namely, what about variables and constants? And here, for simplicity, so this is for function calls here, how to translate a function call. If you have just a single variable, we translate it to 0. We assume that accessing a variable takes no time. You could also translate it to 1, then everything just becomes, the constants become a little bigger. But for the same reason, for simplicity, we assume that the time it takes to evaluate a constant is also negligible. That still leaves some things, namely, how do we deal with things that aren't explicitly defined, like constructor functions. and like primitive operations on numbers and booleans that are already in the prelude. And here we make the following simplifying assumption that constructor calls and primitive operations on bools and numbers cost simply one time unit. That's not unusual that you work with a unit cost model where you don't care about how large things are. You just say it takes one time unit to evaluate an addition or something like that. So that's the full, not quite, that's the almost complete definition. Since I don't see any confused faces, I'll just continue. So here is an example. If this is our defining equation, the append function of the empty list and y's is y's, that's translated into time for append of these two arguments is 0 plus 1. Where does the 0 come from?
Evaluating y's.
Yes, exactly. Accessing the variable takes 0 time, and the plus 1 for the function call, exactly. And the second one is the application where the first one is a cons, and then we pull out the cons, so to speak. And here it's a bit more complicated. So this 0 is for accessing the variable x. Then this cons causes 1. We assume that the cons constructor takes time 1. Then we have x's and y's, which take time 0 and 0. Then we have the time for actually computing the application here. So that's this time here. And then finally have the plus 1 for the function call on the right-hand side. No, the left-hand side. So it's a purely mechanical procedure where you just go through the turning. And you can actually simplify the procedure, at least intuitively. It's not mathematically it doesn't become simpler, it's just easier to remember. How do we translate an expression into its time expression? Well, we just say the time expression is the sum of all time functions applied to arguments S1 to Sk if some subterm of E is of the form function call with that arguments, you simply take the time function with that arguments and you sum up over all of them. So you basically go through the expression, you look at every sub-expression and you sum up how long does it take to evaluate that sub-expression, and then you add all of them up. That's all there is to it. And the previous slide was just a more precise or more structured way of writing the same thing. And of course, if one of the function calls is a constructor or a predefined function on bool on numbers, then we simply assume that the timing function gives us back the result 1 for that call. So this one may be easier to remember, this way of writing it. But this only works if we don't have if then else and case constructs, because they break the modularity. So far I've assumed that everything is more called by value semantics. I've always assumed if you have a function call, well, how long does it take to evaluate that function call? You have to evaluate all the arguments and then the function call itself. So that's clearly a call by value assumption. Now, if then else and case constructs don't have that feature, they don't need to evaluate all the arguments, they'll only evaluate one argument first and then decide which of the others to evaluate. Conditionals and case constructs are evaluated lazily, and we have to model that. So we have to augment the rules that we had so far with new rules for if then else and case. And I think I will just look at the if then else. The case is completely analogous. And this is the if then else. So if we want to time an if-then-else call, so translated to its time complexity, that will be t plus. What is t? T is the time it takes to evaluate the test. And then we have S1 and S2, the two branches, and they are translated into T1 and 2T2, but you don't just add both of them together, but you add conditionally, if B is true, then you add T1, and otherwise you add T2. So that reflects precisely the operational semantics of an if-then-else, where you first evaluate the T, so that time you have to spend, and then first evaluate the B, which takes time T, and then you decide based on the value of B if you also evaluate T, S1 or S2, taking time T1 or T2. So if you have if or case constructs in your expression, then the previous slide with the simplified version doesn't work anymore, because the previous slide assumes you take the term T and then you just go through all the subterms and you sum up everything. That will be too big. I mean, it'll still be an upper bound, but it could be just much too large an upper bound, and therefore this simplified version only works before we considered if-then-else and case. And once you have if-then-else and case in there, then you really need this structured version that goes through the term recursively and does something special for if-then-else, and rather than just summing up everything. Yeah, similarly for case. Now, it is legitimate to simplify things further. I will just mention one simplification. Essentially, where although we seem to be computing precise numbers, in the end, we're really only interested in order of growth, but we don't want to pull in an explicit O operator. So it's okay to reduce constants. Namely, if you have an additive constant, like plus 3 somewhere, then it's also okay to just write +1. So here is a simple example that if we go back to the original definition of the timing function for the append equation, where the first is a const, then we have, I think, on the right-hand side +2, but it's perfectly okay to write +1. There's a constant factor between the two versions, the one with +2 and the one with +1. This one will be only half as big, the result, as the other one, because you've pulled out a constant of 2, a multiplicative constant of 2 out of the whole summation process. So it's okay to use this equation because in terms of O of, you're still in the same league. You've just multiplied or divided by a constant the overall complexity. It is also okay, actually, in some cases, in some base cases, to reduce the constant from 1 to 0, but that's more difficult to justify. Okay. I was surprised that 2 people simultaneously wanted to tell me something or had a question. I thought, have I done something wrong? Okay, the projector is projecting again. So this is okay. Now, just a general discussion about this whole approach. So, of course, there's a danger when you produce TF from F that you make a mistake somewhere, and so this whole process can be automated. And indeed, if somebody is still looking for a simple kind of project, there might even be people looking for a bachelor's project, then in this context, it would be nice to do something to automate more of the process. Now, even if you automate the definition of TF from F, there's still the question if you write some piece of code that takes the definition of F and produces the definition of TF, is that code correct? And so what you could do is you could also have a semantics for your functional language, a semantics with some kind of timing annotations, and then you could really prove that the timing function has the time that the semantics for F dictates. You can in fact justify what you're doing, not just on paper, but you can also justify it with some formal semantics for this little language we're using to write down our functions. However, of course, all of this is very abstract and it's an abstract model, and if you really want to have precise complexity bounds, that means something on some machine that you're going to execute it on, then this is really a hard problem. Then you would require a formal model of at least the compiler and the hardware, and it can be done, but it's a lot of work. It's kind of, we're just scratching the surface here, and we're just at the same kind of level that an algorithms course is, where you also don't really make very precise assumptions about the machine, but you just say, oh yeah, this is kind of within a constant factor, this is probably going to work out. But if you want more, then you need these formal models of more of the things that are involved in executing code. Yes?
Could you please elaborate the second point, where you say we need to have semantics that count computation steps, but aren't we doing that in the TF function?
Yes, but there is, as somebody already pointed out last week, there is no formal connection between F and TF, in the sense that there is some independent semantics of F that tells us this is how how long this function takes. You're imposing that semantics, but you're imposing it through a piece of code that translates F into TF. And so this piece of code is not part of a logical definition, it's just part of the infrastructure for translating one to the other. So in some sense that does provide the semantics, but it's not something you can reason about because it's not part of your logical setup, it's a different level. The difference may look negligible, but if that translation process becomes complicated, then you may want to justify what's going on, and rather than just saying, like semantically, this translation process from F to TF is the semantics. You might want to have some independent document that's easily sort of or you can audit it and you can say, oh yes, this is what I believe. Whereas a piece of code that does some translation is usually not the best formal definition. Okay, so now let's apply this. Well, we did already apply it actually last time, so we're not going to go through that again. I did it in the other order for certain reasons. So we already covered insertion sort complexity, and we will now instead go on to merge sort, which is a bit more interesting. And this is the well-known merge sort function. So it's based on a function merge that takes two lists and merges them of course, we assume implicitly that the type A of elements in the list is a linear order again. And the merge, once one of the lists is empty, just produces a second list. And if they're both non-empty, then of course you have to check if they check the first two elements and pull out the smaller one and then recursively merge the tail of that list where you have removed an element and the other list that you haven't changed. So it's a standard function, and then merge sort takes the list to a sorted list. And what is it? How is it defined? Well, if you have a list of length 0 or 1, then it's just the list itself. And otherwise, you have a recursive call of merge with two sublists. Namely, you take, this is X is the input list, and then you take the first n diff 2 elements. So take as the standard function that, given a length and a list, takes the first n elements of that list. And similarly, in the other branch, you drop the first n diff 2 elements from the input list, and then you recursively and independently merge sort them, and then you merge the result. So I do assume that you've seen something like this in a functional imperative language before. And so now we will analyze the running time complexity. Well, actually, no, we won't. We will analyze something simpler, and as is done in all the algorithms textbooks, we will analyze the number of comparisons. Because if you actually analyze the running time, it's a much more complicated expression, and it's not so nice to analyze. The result would be the same, but it takes a lot more work, and so we simply analyze something that's easier to quantify, the number of comparisons. So let's move over to the file. Is that it? No. Yes. That's nope. Probably not. Is that it? Yes, that's it. So you have to tell me if the font is too small, then I can enlarge it. But as long as nobody complains, I'll leave it like that, because then we can see more on the screen. So this is just the merge function as we saw it, and here is the merge sort function. And you see in both cases I have explicitly said that the type A is a linear order. And now, here we count the number of comparisons only. And so we can now look concurrently at the function merge and C merge, so the comparisons that merge requires. And if you look at the first two lines of merge, there is no comparison. And then in the last line, of course, there is one comparison. That's where the 1 plus comes from in the C merge at the bottom. And then you again have the same expression, the same if then else, if x is less than y. Then, well, then it's the number of comparisons in merge, in this recursive call of merge. So it's this one here, C merge of this, else it's the number of comparisons in the other merge call. So we have simplified. The timing function would produce a bigger number, but it's easier to analyze just the merge, the number of comparisons. So first little test, what is an upper bound for the number of comparisons of two lists, x's and y's? Pardon?
Four comparisons.
The result of C merge, as it's defined. And yes, that's all the comparisons that the function merge will do when it merges x's and y's.
All comparisons that are possible between two lists.
No, I mean, hang on. Then I think you haven't quite grasped what C merge does. C merge counts the number of comparisons that merge will do when it merges x's and y's. That's why C merge is defined completely analogously to merge. Yes?
most the maximum of the length of axis and y.
Right. Max length axis and lengthwise. And we get a little note here, a blue note. So what does it say? Auto quick check founder counterexample. So who can do better? Yeah.
You can just add the two lengths.
You have to add the two lengths because you really may take it may in the worst case take the length because in each step you just drop one element from these two lists. Yeah. And then, indeed, this can be proved automatically. It is really at most the length of the two lists added together. And then here is the comparison function for merge sort. And I'm not showing you merge sort again, but let's just look at it independently. I think it's fairly intuitive. So how many comparisons does merge sort take on a list axis? Well, first n is the length of axis, y is you take the first n diff elements, z is you drop the first n diff elements. So this is just the same thing here as in merge sort, except that I've pulled out more in a let. Here in merge sort, I just used the let to remember the n and didn't pull out the take and drop terms down here. Here I'm doing that, and then, yeah, if the list is length of the list is less or equal 1, then there are no comparisons because it's just the output list, and otherwise it's the number of comparisons for the two sublists that the merge sort takes in the recursive call, plus the number of comparisons that merge takes. This is wrong. Yeah. Oh, right, there's a 1 missing because we have at least this comparison here. No, hang on, there's no 1 missing. No. If you look at this expression, all the comparisons in this expression come from the two recursive calls of merge sort and the merge. So there's no +1. We're just counting comparison. There is no comparison. Oh, sorry. I meant comparisons between elements. Yeah. Yes. So I should, doesn't it? Oh, yeah. We count the number of comparisons between elements. Yeah. So, but it's still, I still made a mistake. So if you compare that call with, unfortunately, let me see, if we remove this, then we can see the merge sort, at least the interesting bit, and the CN sort. So the last line the first line at the top and the last line at the bottom, they don't quite fit together. What's wrong here? Yeah.
You have to merge the result of the sorting.
Yes. So this is wrong here. I'm not comparing y's and z's, but I'm comparing the sorted versions of y's and z's. Now, in the end, of course, that shouldn't make any difference. Why? Because we have this upper bound here that the number of comparisons when calling merge only depends on the length, and we can prove that the length is not modified by merge sort, but it's just wrong. And this is the kind of mistake that one can easily make if you do it by hand. Now, let me see. I would prefer not to correct that now, but see if we have some time at the end and come back to it. And just go through the version that I've written down, which isn't quite correct. That okay? Then let's just look at the main proof, or first the main statement, and we will only prove the comparisons, number of comparisons of merge sort in case the list has the length of the list is a power of 2, because otherwise the NDiff2 does funny things, and it just gets more difficult to do this estimate. This is the simplest version. And I'm also avoiding logarithms by using 2 to the k. So here it says if the length of the list is 2 to the k, then the comparisons of when sorting that list with merge sort is less or equal k times 2 to the k. So if you were to take if you were to replace the 2 to the k by length of x's, because that's the assumption, 2 to the k is length of x's, then you have length of x's times k, and k would just be the log of the length. So then you have the well-known n log n, but I'm rewriting it to avoid the logarithm into this exponential format. So it's saying the same thing, but not using the length, but using the 2 to the k instead of the length, and then things become simpler. And when we prove that, well, we'll prove it by induction on k. So for an arbitrary list x's, and for the base case, if k is 0, that's all trivial. And so let's home in on the induction. If we're looking at the k plus 1 rather than k, and we're also we can ignore the case if the length of the list is less or equal 1. So we will home in on this case where the length of the list, if this is false, if the length of the list is greater than 1. And then we have this, in the end, it's just this set of inequations. And so you start out, how many comparisons does merge sort take? Well, then you just unfold the definition of the comparison function, and it tells you that's the number of comparisons of merge sort of the two sublists. So here in the proof, I've also abbreviated question mark y's is the one sublist, and question mark z's is the other sublist. And so the comparisons for the whole list x's is the comparisons in merge sort for y's and merge sort for z's, plus, and this is where the mistake comes in, the number of comparisons when merging y's and z's. But at least if we accept that this is wrong but would lead to the same result, then we can continue, and then we can invoke the induction hypothesis for these two merge sorts. Why? Because we're doing the induction on k. This is what we're doing the induction on, and k is used here with the assumption that the length of x's is 2 to the k. So if we halve the list, then of course it'll just be 2 to the k with one smaller k. And so we can use the induction hypothesis on this one and replace this term with k times 2 to the k using the induction hypothesis instantiated with the list y's. And then we do the same thing here. This subterm, comparison merge sorts for z's, we can also replace that by 2 to the k times 2 to the k, using again the induction hypothesis, but now instantiated with the sublist z's. And then we are left with this term here, the comparisons number of comparisons in the call to merge, and then we use that is bounded by the sum of the length of the two sublists that we're merging. And again, we're using the lemma in the next line. We're using that lemma that tells us that the comparisons in merge are bounded by the length of the two lists. And then we're almost there. so we get to this point where we have, what do we have? 2 times k times 2 to the k, that's for the 2 sublists, the complexity, plus 2 to the k. Where does the 2 to the k come from? Well, that's the sum of the length of the 2 lists. We assume that the 2 sublists have length 2 to the k, and we're adding the 2 lengths, and so you get 2 times 2 to the k. And so in the end, we have proved that the comparisons of merge sort for this list are less than or equal this expression. And why is this what we wanted? Well, oops, no chalk? Yes, chalk. Because we want to prove in the end that the comparisons of merge sort for x's is less than or equal. Now x's has length k plus 1, so it's supposed to be k plus 1 times 2 to the k plus 1. And if you multiply that out, then you get exactly the expression that we have here, 2 times k times 2 to the k, because this is, of course, 2 times 2 to the k, and if you multiply that with that, then you get exactly that expression. So this is a really very straightforward chain of inequations where you simply use the induction hypothesis for the 2 sublists and the estimate for the auxiliary function merge. And that's it. Well, except that maybe you want to rephrase it after you've proved it in this format. Maybe you want to rephrase it in the customary format with the n log n. We can do that. This is how you can write it. Oops. So if the length of x's is a power of 2, then the number of comparisons in merge sort is bounded by length of the list times log 2 of the length of the list. And that will be a direct consequence of this version here, just using some trivial properties about logarithms and exponentiation. But it's not all as simple as it may appear. For a start, if you write that down, it looks very nice. But if you look at what the system makes of it, it doesn't look quite as nice anymore. No, this is not what I wanted. So if you compare your input statement, the lemma statement, with the sub-goal, then you see that the system has inserted lots of conversion functions from from natural numbers to reals, the function real, which it must, because otherwise you can't take logarithms. The logarithm produces a real number. And therefore, that already complicates things. You now have these conversion functions, and you can't now reason as simply as you would on a piece of paper, where you normally don't have different numeric types, but you just have, as in mathematics, one numeric type. And then, in fact, you have to use of course, you have to use this lemma here. So that's this lemma here that you see at the bottom. But now, if you just apply simp, not much would happen. So you need some lemmas, and then you still don't get there. After the simp step, you're still left with something, if you look at the bottom, that looks like it's almost there, but not quite. Here we have the expression, our estimate from the previous lemma in terms of k times 2 to the k. And here we have almost the same thing, but here we have a version where the k has been converted to a real number. And so it's not, the proof is not automatic here. At least I don't think it is. If I ask by arith, I don't think it can do it for some reason. Yeah, it can't. And so we have to call a sledgehammer, and sledgehammer finds some strange proof here involving all these conversion functions and how they interact with multiplication and exponentiation. And then in the end, you can prove it. So I'm just showing you there's a reason why we're trying to avoid logarithms, not because they're mathematically complicated, but because the framework that we have with these different numeric types introduce technical complications that I would prefer to avoid as long as possible. Of course, there will be points where we have to use the logarithm, but I'm just warning you, these conversion functions are really a bit annoying, in particular if you have some lemmas that are stated about natural numbers and you want to use them in a context about reals. If everything is stated in terms of reals, you're okay. But if you have this mixture, then it gets ugly. So that was just a kind of a hint of the complications that can enter the picture if you mix numeric types. No, it's not it either. Yes. So now, that was all I wanted to say about sorting. And so now we close the sorting chapter and we get on to binary trees. And today I just want to talk about a few simple properties of binary trees that don't have anything to do with sorting yet. Next time we will get on to interesting versions of binary trees, namely 2-3 trees and red-black trees, and how, not sorting, but how they can be used as indexing structures and why they work. So today just ordinary binary trees and some combinatorial properties of those. They live, part of that stuff that I'm talking about today lives in the Hall library in theory tree, and there is some additional stuff that is in the Bitbucket repository for the course in this subdirectory. And we had already seen the binary trees, just for to remind you, with the two constructors leaf and node, and the abbreviations with the angular brackets for the leaf and node construction. And when I say tree, most of the time I will mean binary tree. So, basic functions, we had also looked at some of them already, so I will just go through them quite briefly. There are the traversal functions that turn a tree into a list, and in particular the in-order traversal, where the element at the root of the tree is in the middle of the list, and you have the elements left and right at both ends of the list. And similarly, there's pre-order, where the element at the root of the tree is at the beginning of the list, and there is also post-order, where the element at the root of the tree is at the end of the list. So I assume those notions are all familiar, and the function programs are easy enough to grasp. So then there's the size function that tells us how many nodes are in a tree. So the size function of a leaf is 0, and of a node it's the number of nodes in the left and right subtree plus 1. Now I'm using on the slides the shorter, the abbreviation with the absolute value function applied to the tree, but this is only on the slides. In the theory you have to write size. That's the proper name, and the vertical bars are only for a short notation, are just a short notation. And then we have size 1 that doesn't count the number of trees, but not the number of nodes, but the number of leaves. Although it's defined in a non-obvious way, it's defined just by adding 1 to the number of nodes. But if you're familiar with the with binary trees, you'll know that there's always one more leaf than there are nodes in there. And in fact, from that definition here of the size 1 function, you get exactly the recursion equation that you would expect. Size 1 of a leaf is 1, and size 1 of a node is just the sum of the size 1 functions of the subtrees. And I will be using both functions, both this one and the size without the 1. One is naturally, sort of come from discrete mathematics, you're naturally inclined to start counting at 0. And so that's why the first size function is from that perspective, the more natural one. On the other hand, if you come from continuous mathematics, you're used to taking logarithms, and if you take logarithms of 0, then you have a problem. And so that's why both of these functions are useful. So. Yes, yeah, that's all. Yes, said that. So we also have a height function. What's the height of a tree? The height of a leaf is 0, and if you have a proper node, then it's just the maximum of the two heights plus 1. And again, on the slides, I will use this short version, h of. In the theories, you really have to write height. And of course, the height of a tree is bounded by its size. That's pretty obvious. And the other one you have proved in one of the exercises already, that the number of leaves in a tree is bounded by 2 to the height of the tree. We will also introduce the minimal height for one specific reason. So the height is, in some sense, if you have some arbitrary tree, the height is the length of the longest path from the root to a leaf, and the minimal height is the length of the shortest path from the root to a leaf. And so it's like the height, but you take in a node, you take the minimum of the two minimal heights and add 1 to it. And again, we use the MH abbreviation only on the slides. And the minimum height, of course, is less or equal to the height, and the minimum height is a lower bound from the number of leaves. So when we look at the height, the number of leaves had an upper bound 2 to the height, and the number of leaves has a lower bound of 2 to the minimum height. And this is another interesting one, the internal path length of a tree. That's the sum of all the length of all the paths from the root to a leaf. For the leaf itself is 0, and for a node, it's this funny formula. Well, it makes sense that you take the internal path length of L and internal path length of R. But then those are too short. Each path in L and R is just short by 1, because you want to count from the root and not from the root of the whole tree. So what this does, when you also add the number of nodes in L, you're adding 1 for each node in the subtree, and that's just the one that's missing because you came from the larger tree. And you're doing the same thing on the right side. So there are alternative definitions that do things differently, where it's maybe more obvious that this function, that the function IPL really computes the internal path length. But I hope my explanation also convinced you that this is also a right definition. Yes.
Could you please elaborate what is internal path length?
Internal path length is the length of all the paths from the root to a leaf. To a leaf, to all the leaves. The sum, yeah. So if you have some tree like that, and let's assume let's assume the dots here at the end are leaves. Then the length of the path, it should be 2 plus 2 plus 1. I hope that's right. It's always very easy to get off by one, but I think it's correct. And so it would be, so here it's 2 plus 2 plus 1, and how does that definition do it? So IPL, let's call this T and this T1, and this, yeah, let's call it T and T1, that will, T and T prime, that'll do. And so IPL of T is therefore the IPL of T prime plus IPL of this one, but that's 0. And so what is IPL of, hang on, no, and plus the sizes. Plus the size of T prime plus 0 plus the size of, well, that also 0. So yeah, that. Now, the IPL of this one is IPL of that one, which is 0, plus the size of that one, but the size is, I think I did make a mistake with the plus 1. We are off by 1. I think this will just, it will come out not as 2 plus 2 plus 1, but 1 plus 1 plus 0. I think that's what's going to happen. So here we have 0 plus the number of nodes in, oh no, the number of nodes, yes, the number of nodes in T prime is 1. Sorry, IPL of T prime is the, this one plus IPL of here and here is 0, and the number of nodes in there is also 0. So all of this is 0. So this is just 0. And here you get 1. And I think that's because the only thing that counts is really this one. So then it's the number of the length of the path from the root to all nodes, or to all leaf nodes. Yes, I think it's to all leaf nodes. So nodes that are directly above leaves.
I think it's an artifact of our construction that we always have these empty leaves at the end.
Yes.
And node,
yeah, there's also an external path length, and that, in fact, yes, the internal path length is the length of the sum of all the paths to the leaf nodes. That is nodes that don't have any other nodes below them, and the external path length is actually that's the sum where you go to the leaf themselves. So why is this relevant, this measure? Why does that tell us something about the tree, about the search tree? If we assume that all the elements I'm now confused myself, because I wanted to motivate it by saying it's the average time it takes to search an element in the tree. If it's a search tree, and I think that is not true, or rather that is probably true, but my motivation for this IPL was wrong. Because here it seems we're only adding up the path to the leaf nodes. Yeah.
Maybe if you divide it by the number of leaves, then it becomes
Yeah. Sure. You have to divide it by the number of nodes, I would think. But it would then have to be to be what I think it should be. It would have to be the sum of all the path from a root to any node, and not just to leaf nodes. Because when you search, you'll search any node in the tree. So is this, by any chance, is this what this is?
But this one gives us an upper bound on it, right?
Yeah, no. This is only, I mean, these we're not counting search path from root to some arbitrary node.
So I mean, when we divide this by number of leaf nodes, then it will give us an average case of search, upper bound of search.
No, it won't, because we're ignoring the searches that. Oh, an upper bound. You're right. Yes, because that's the worst case if we always look only for leaf nodes. Yeah. But I think I have to work on my motivation here. Why this is an interesting function. Yes, so let's just leave it as it is, and I'll have to look at it in, without standing in front of the class. So, in fact, I think then it's better to just jump over all of this and go to complete and balanced trees, because that's another important property, and that's more intuitive. So when we call a tree complete, basically when it looks like a triangle. So all the leaf nodes are at the same height, at the same depth. And there are many ways to define it. This is the one I've chosen. A leaf, of course, is complete, and a node is complete if both subtrees are complete and their heights are the same. And then we get a number of consequences of that. So the first one is that a tree is complete if and only if the height and the minimal height are the same. That's where this view of a triangle makes sense. And another nice implication is that if a tree is complete, then it's actually 2 to the height many leaves. And this is, no, I don't think I want to do this one. I want to do the other direction. Yep. And the other direction is also true if it has, if the number of leaves is a power of the height, 2 to the power of the height, then the tree is complete. And so it's really an equivalence, completeness of the tree, if and only if the number of leaves are 2 to the height of the tree. And this direction I would like to look at in more detail. Or rather, actually, no, I don't think I will. I want to get on to more interesting things. So it's just, the proofs are by induction, but you always have to figure out what the best thing to induct on is. And I would really like to get on to search trees. And also the same is true for the minimal height. If the number of leaves is 2 to the minimal height, it's also a complete tree. And if it's not complete, then there are actually fewer leaves in there than 2 to the height. Yeah.
Why did you formulate the third and fourth letter as a consequence and not as a quality?
These two here.
It seems to me that they would also be quality, right? No, it isn't. Right? No. Because they actually lose precision by using maximally.
Hang on. Well, we do once. This is one direction, and this is the other direction. So the two of them together tell us that it's equivalence. But I think the proofs probably work differently for the two directions, and that's why I did it differently. I think that's only why I did the two implications. And this one, the last one, I presume is may not be an equivalence. If it's complete.
Doesn't the last
Oh,
one-
yeah. The last one is. Pardon?
It follows from the first level.
Yes, indeed. Yeah. So they are all equivalences, but I think these are, I stated them as implications because the proofs of the separate directions seem to work simpler. But if the tree is not complete, then we have that the number of leaves is really strictly smaller or strictly larger than the minimum height. 2 to the minimum height. And for whatever it's worth, you can also work out, I got this from Knut's book, the internal path length of a complete tree of height h, namely that's h minus 2 times 2 to the h plus 2. And let's not worry about the proof, but now we come to this application that the internal path length has something to do with the average time it takes to search a tree. And yeah, in search we find the node labeled x takes as many steps as the path from root to x is long. Thus, the average time to find an element that's in the tree is IPL of t divided by the number of nodes. So this is the argument we were making earlier on. I was just getting unsure whether IPL really is the number of all the paths or whether it just goes to the root nodes. That's what confused me. Now let's assume we have a complete search tree of height h, and that means we have this internal path length, and so if we now divide that internal path length by the size of t, then you find that this approaches asymptotically h minus 2. So in a complete binary search tree, you really have the average time is of the same order as the height of the tree. And why is this h minus 2? Why does that come out of this formula by dividing it by the size of t? Well, the size of t is just 2 to the h, give or take 1. So if you divide this expression by 2 to the h, the 2 to the h drops out. And I think there's a... why is it not... Oh yes, and yes, this drops out. This just becomes 1, and this goes to 0. And so the whole thing goes to h minus 2. But this is only for a bit of education. It's not something, I mean, I've done it formally in Isabel, but I'm not including this here because then I would need to introduce some such notation as this formula grows asymptotically. It has the same order of growth as this formula, and I don't want to go into that. That's too much, sort of too far away from the algorithmic part. And this again shows that having these different numeric types can be a headache. This all worked very well on the slide, but this isn't actually correct if you interpret the h over type nat rather than type int. Because if h is a natural number and you subtract 2, then you get these boundary cases. If h is 0 or 1, it stays at 0 or 1, and then the formula becomes false, and then you have to, actually, this is how you have to write the formula, and so this is really what I proved with conversions from nat to int, and then it works again. So it's again a situation where the numerics gets in the way. So it's a question whether I should have covered this at all, because it really leads into complications I don't want to get into. Balanced trees are just short of complete trees. So here we say a tree is balanced if the difference between the height and the minimal height is just 1. And so you can think of it not as a triangle, but sort of the triangle where the two bottom, at the bottom you have two different levels of leaves. But that's the only, it's sort of a triangle that's kind of a little bit rugged at the bottom. And then you can actually show that balanced trees have optimal height. So if you have a tree is balanced and you have another tree, T prime, that's greater or equal in the number of nodes, then the height of that tree, T prime, will also be greater or equal than the height of T. So that means we're always, when building search trees, we're always looking for the search tree, always looking for balanced search tree. Why? Because then the height of the tree is minimized. And yes, the way I'm using complete and balanced is not standard, because the literature is simply not standard. If you look for balance, then you get a number of different definitions of what balance means, and sometimes complete is called perfect, and so there's no uniform terminology here. I'm using a particular one. Yeah, so what Knuth calls complete, we call balanced. Yeah. So now that was all I wanted to say about these general combinatorial properties of trees, and now we move on to search trees. And I will just start today, and the more interesting bits come next time. So we will start today with unbalanced binary search trees. And we focus on BST's binary search trees, but then next time we will also have these 2-3 trees, which aren't really binary. So what's the idea when you have a binary search tree? In essence, it's just an implementation of a set. So which set does a tree represent? Well, here is the function set tree, so it converts a tree into the set that belongs to the tree, and of course the leaf represents the empty set, and a node represents the union of the elements in the left part and the right part and the element itself. And so, although we work with trees, the thing that we're trying to achieve is really operations on sets. And that's really the idea of a binary search tree, that you can search for elements in time O of height of the tree. And this function set tree is just an instance of something one calls abstraction function. In computer science, in particular in data structures, you all the time have the situation, you have some concrete data structure that represents some abstract mathematical concept. And here, in this case, the abstract mathematical concept is the set, the concrete data structure is the binary search tree. And the mapping from the concrete level to the abstract level, that's usually called an abstraction function. And what is a binary search tree? Well, we define it like this. Of course, a leaf is a binary search tree, and if you have a node, it's a binary search tree if both subtrees are binary search trees, and if all the elements in the left part are less than the element in the middle, and all the elements in the right tree are greater than the element in the middle. So that's the recursive definition of binary search tree. And we again assume here that our type of elements in the tree is a linear order. And if we use natural numbers, integers, and reals, then they are linear orders, so they fit into that framework. So what's the interface that we want to give to the client of our binary search tree? Well, it must be the same kind of interface as for sets, and it must have first an implementation type. So if you implement sets, you will implement them by some type S. And then you expect to have a function empty that returns an empty set, and an insert function that takes an element and a set and gives you a new set. And you expect to have a delete function that takes an element and a set and gives you the new set where the element has been removed. And the isin function that, given a set and an element, tells you whether the element is in the set or not. So this is what what the interface to a set data type should provide at the very least. Of course, there are many more functions you might want to have in there, but we will focus on this minimal interface. Of course, you might also implement a map rather than a set. And if your type implements a map from type A to type B, then you would expect the following functions. Of course, you have an implementation type M. You would have an empty map. You would have an update function that takes an element A and B and a map and updates the map to map this element to this result. And you have a delete function that removes an element from the map. And you have a lookup function that, given a map and an element, gives you back the element that this argument is mapped to. And of course, it's an option because it might not be mapped to anything because it's a finite map. So sets, of course, are special cases of this map type, where the type B is simply the type of Booleans, where you map elements to true or false, whether they are in the tree or not in the tree of the set. And so we will ignore the map most of the time, and we will just use the set interface. But it's usually a trivial extension if you have something that implements sets, at least if it's something like a search tree, to upgrade it to implement a map. How do we go about comparing elements? Well, just for aesthetic reasons, not really for formal reasons, we assume, of course, that the elements are linearly ordered. I already said that. And instead of using the less than and less or equal directly, we introduce a new data type comparison value that has the constructors less than, EQ, and greater than, and then we define this compare function, and if x is less than y, we return less than. If x is equal to y, we return EQ, and otherwise we return greater than. That just lets us write the code a little bit more nicely. And of course, you don't have to implement the comparison function that way. Whatever type you have may directly give you a comparison function that doesn't need to make these primitive comparisons and make two comparisons, but could do it in one. So now, unbalanced binary search trees, what do they look like? Well, you're familiar with those, I'm sure. So here, the implementation type of the set interface is a tree over type A, and the empty set, of course, is just a leaf. That's why it's normally not mentioned even. And the insert function, well, if you insert into a leaf, you just get this singleton node, and if you insert into a node, then depending on what the comparison tells you, you either recursively insert in the left or insert in the right, or just leave the node alone if it's already in there. And the isin function is a similar recursive descent through the tree to search for the element. And the delete function, that's the only thing where you have to do a little bit of thinking. Of course, the empty tree, you can't delete anything from there, it just remains empty. And otherwise, if you have a node, how to delete an element from a tree with a node A in the middle? Well, one way is to delete in the left part or delete in the right part, if it's in the left or the right part. But interesting, of course, is the question, if you want to delete the element in the middle, what you do, and then you can do the following. You basically look at the right, you want to delete this A. Now, if R is already an empty, then you can just return L. But if R is non-empty, what you do is you call a function delmin that gives you the minimal or the leftmost element in the, in here of R, and then you put that into A. And it gives you, delmin gives you back two things. It gives you back that minimal element, and it gives you back the remainder tree that's left over after you've removed the minimal element. And then you build this as the result tree. And the delmin function is just, it walks down the leftmost, the left spine of the tree, and as soon as it gets to the end, then it can return if L is empty, then it can return A and R, and otherwise you have to do things recursively. So this is really all undergraduate material. And now the question arises, what does it mean that this implementation is correct? And this is what I want to focus on in the remaining 5 minutes. Why is the implementation correct? Well, the claim is that the implementation of empty, the leaf, simulates the empty set, insert simulates the union operation with a single element, delete simulates a minus operation on the set with a single element, and is-in simulates the element operation. So we're justifying our implementation with respect to the behavior of the element of the functions on the abstract level. Yeah.
So the semantics of the set minus is that if the element is not in the set, it just doesn't do it.
Yes, there are no negative elements.
No, it just maybe it's not applicable if it's not in there.
No. Sets are very well behaved. You can remove things that are not in the set and then nothing bad happens. So what does that mean, really, that the upper line of operations simulates the lower line of operations? Well, it means that if you apply the abstraction function, you get from the concrete level to the abstract level. So if you apply the abstraction function set tree to the empty to the implementation of the empty operation, you should get the empty set back. And of course, empty is just the leaf, and set tree applied to leaf was the empty set, so this works. But similarly, you should have the following, that if you insert an element into your tree, and then you get out the elements instead of all the elements, that should be the same as the elements beforehand, plus this new element. So this is exactly what I'm saying up here, that insert implements this union with a single element. And similarly for delete, here it's the subtraction with a single element. And the set tree is always the mediating function that maps from the implementation level to our abstract mathematical model. And is-in should just have the same behavior as if you use the element, mathematical element operation on the elements in the tree. This is almost correct. We want this, but it's enough if this is only true for binary search trees. So under the assumption that T is a binary search tree. Because otherwise, these functions will not operate correctly. If it's not a binary search tree, then the implementation is incorrect. So the implementation assumes that things are ordered, the tree is ordered. And we also must prove that the functions preserve this property, so that you start with the empty tree is a binary search tree, and if you start with a binary search tree and insert an element, you get again a binary search tree, and similarly for delete. So that's always this game that you have some functional properties that you want, that the operations behave like some abstract data structure, and then you have the preservation of invariant that you need as well. And because otherwise, after a few steps, you may lose your invariant, and you can no longer assume it, but you need to assume it to prove these properties. And this is the standard way of proving correctness in this specific case of the of some tree implementation with respect to some the abstract data type of sets. But what you see works in general for different kinds of interfaces, as long as you have this abstraction function that maps some concrete implementation to some abstract level, and then you have to show that the concrete operations behave the same as the abstract operation if you apply the abstraction function to them. That's the general idea here. And with that, I want to close for today. yeah, see you Friday. Yeah, the question, yes.
So I've seen in the tutorial documentation of Isabella that we also define inductive definitions for.
Right. There are also inductive definitions rather than recursive functions, and we don't need them in this course, and that's why I haven't introduced them. I think it's just we only have 2 hours a week, and so I cut out the things that aren't strictly speaking necessary. But what, did you have a specific question about them?
Yeah. Can we replace the functions where we written rules with the inductive definition?
Where?
So, for example, Eason. That is
right. Well, this for me is a function that I want to provide as for my client, and so this is really a program. So here I don't want an inductive definition. In fact, the general rule is if you can write down the thing as a recursive function, it will be easier to use than if you write it as an inductive definition. But there are sometimes situations where you can't write it as a recursive function, then the inductive definition is the right tool. Okay, since those were all the questions, then see you again coming Friday.